In this video, I want to introduce harmonic oscillator as one of the best well-known and also most illustrative examples of quantum evolution. But before we jump into quantum mechanics of harmonic oscillator, we have to review for consistency and for convenience also the classical results about and around harmonic oscillator. So one thing about harmonic oscillator is that it has very simple and very characteristic Hamiltonian. Hamiltonian is an classical, obviously classical in this case still, function which comprises the energy of the system. So it has the potential, the kinetic energy, which is given by the momentum square divided by twice the mass of the particle which is oscillating. And then there is m omega square, where omega is the frequency of the oscillator divided by 2, and here we have the coordinate q to the second power. So the potential looks like a parabola. Here we have the coordinate q, and in this case here, where the potential has the minimum, is 0. In fact, in this particular case, this is the potential energy, and here is 0. So 0 point is down here. Now, to make the treatment a little bit simpler, we will introduce a different coordinate where we will try to get rid of some m's and omegas. So we will introduce coordinate q bar, this is just a change of units of the length. So this will be a new coordinate. And now I will use some knowledge from theoretical mechanics, which tells me, well, if I have this new coordinate, how to find a corresponding conjugated momentum. And that I do by, you can basically forget about this if you are not interested in details. So I will define a Lagrangian, which is now a difference of the potential and the kinetic energies, or kinetic and the potential energies, and they have to be now written in terms of coordinates. So originally this was something like m q dot, the time derivative of the coordinate square divided by 2. I mean, if you remember that momentum is m multiplied by the speed, that is coordinate time derivative, then it's clear where this term comes from. And now instead of plus, as we had in the Hamiltonian, we have minus m omega square divided by 2 q square. So out of this thing, out of the Lagrangian, I can, as well as from the Hamiltonian, I can find the equations of motion, but in terms of Hamiltonian formalism, I find them in terms of the momentum and the coordinate, and in this case here with the Lagrangian formalism, I find them in terms of the coordinate and its time derivative. So then it's very easy to define the time derivative of our new coordinate, which will have the same prefactor as the as the coordinate here. So I get that whenever I want to replace the old variable by the new one, I have to just put a prefactor 1 over square root of m omega, and now q dash. So the same thing holds also for the q itself. And the question which we are asking here is, how does the Lagrangian look now in the new coordinates? So this is fairly simple. I just use these definitions here, put them in. So here I have m divided by 2, but then I have a square of this, which means 1 over m omega q bar dot to the second power, so m, I got rid of m minus, here I have m omega squared divided by 2, 1 over m omega, and m goes away and one of the omegas goes away, and here is omega q bar square. So this is altogether 1 over 2 omega q bar square minus omega 2 q bar square. Alright, and now the question is, how do I find the Hamiltonian? First, actually, how do I find the momentum with these units? So question on momentum. It's the conjugated, properly conjugated momentum. Why I am actually discussing this? Well, I'm discussing this because if one wants to go from classical to quantum mechanics, one has to use actually properly the conjugated pair of quantities. So coordinate and its proper conjugated momentum. So that's why I'm showing this. So how do I get the proper conjugated momentum? From theoretical mechanics, it's well known that this is obtained by the derivative of the Lagrangian in terms of the q bar dot, or well, the coordinate time derivative of the coordinate I'm interested in. I have to take the partial derivative of the Lagrangian by this, and that gives me the corresponding p, which is now the p bar. Well, the p bar, when I take this and take the derivative according to q bar dot, that gives me 2 here, 2 q bar dot, and it's divided by 2 omega. So I get 1 over omega q bar dot. That tells me that q bar dot has to be replaced by omega p bar. Alright, so I'll do that. Now with this knowledge I can define Hamiltonian, and Hamiltonian as a function of p and q is defined by some, well, a transformation which is called Legendre transformation, and that's the transformation which tells me which goes this way. It's p multiplied by the it's the p bar multiplied by the q bar dot minus Lagrangian in terms of the q bar and q bar dot. That's how we have it all expressed. But now in this formalism, everything has to be expressed, so I'll do it this way. Everything has to be expressed as functions of p bar and q bar. So here I had q bar and q bar dot, and here I have p bar, but everything including q bar dot has to be expressed in terms of these two guys. So when I use this definition of the Lagrangian, this definition of the p here, and replace all the q bar dots by the corresponding p, I'm getting the following. I'm getting first here p multiplied by omega p minus, from this term I get 1 over 2 omega, and now omega square p bar square, plus the last term is very easy. This is plus because here is minus omega divided by 2 q bar square, and I'm getting, here you see I'm getting omega p square minus 1/2 omega p square. So I'm getting omega half p bar square plus omega half q bar square, and this is my final result. Sorry, I kind of got a little bit ahead of myself here. It's omega divided by 2 p bar square plus q bar square. So that's the Hamiltonian I will be using. Hamiltonian, which will look like, well, I will do one more step in before I start to use it. So this is the Hamiltonian now with a transform of the coordinate, which looks like this. It's q has been transformed into 1 over m omega q. It's just the opposite actually. The Q bar is square root of m omega q. So this is how I got, or for that matter, if I want to go back to the original coordinates, these are the relations. Okay, so here I have ensured that if I take this Hamiltonian and do the quantization in this system, this is still classical Hamiltonian, that I get the proper description, because the P bar is the properly conjugated momentum to the Q. Well, I want to do actually one more thing, and that is I want to go dimensionless. So I will look at the properties of the P bar and Q bar, and I find that I can make them easily dimensionless if I go from the P bars into the P bar divided by H bar. So that's my, I changed the units, I changed the units this way, because if I be using, so that I'm gonna be using these guys, so in order to get them here, I will just add H bar here and H bar here and H bar here, and now I replace these P's, these expressions with just the P, and well, the best would be if I just simply call them P's without the bar. Alright, so now I can maybe even write equals here. So I introduce new coordinates that would look like this, and they will give me the final form, the most suitable form of the Hamiltonian, which looks quite quantum mechanical because it has H bar omega here, but it's still relatively classical. It's actually completely classical. So this is my Hamiltonian that I'm going to use, and the advantage of this Hamiltonian is that Q is now actually perfectly dimensionless, and P is dimensionless too, because this whole thing has a dimension of energy, and the energy is already here, H bar omega, or here H bar omega. Okay, so this is my Hamiltonian that I will be using. Last comment is that this last part, this last replacement of the transform of the coordinates, I couldn't do in terms of this so-called canonical transformation. If I would have right away started with Q defined as, let me sum it up here again, Q is now square root of H bar divided by m omega multiplied by Q. Well, it's very difficult because that's the transformation that we do. So we will go from this, that's a redefinition. I'll put an equal sign here, and you will understand it this way. This is the original Q from which I started, this is the new Q, and the P has a transform which looks, well, somewhat similar, but it has square root of H bar m omega P. So if I would be using this transformation from the beginning, I will never get this form, because P is here now not a properly, well, according to the classical theoretical mechanics, is not a properly conjugated momentum. So I would not be very successful if I try to quantize this Hamiltonian, but we already know how to quantize, so we will not be actually, surprised that it works anyway. The comment is only that I could not do this transformation right away. So with this Hamiltonian, in some of the next videos, I will introduce, or I will quantize it, and I will introduce how to follow, or how to program, how to discuss the dynamics of a harmonic oscillator in the quantum case.